voltage sensor, current sensor, and SD card with RTC. We were given these three sensors as project along with three more optional sensors having a theme. I, Awais Akbar, along with Kamran and Ijaz, chose anti-theft theme. Our first sensor is IR sensor. As soon as a person enters the room where the object being protected is placed, the IR rays will detect the person and alert the security agencies. Our second sensor is weight sensor. A very accurate and precise weight sensor is placed under the object being protected. As soon as the object is picked up, the weight is changed and the sensor alerts the concerned agencies. The third sensor that we are using is IMU sensor. This sensor detects the 3D position and rotation of the object being protected, and any change in position or rotation will alarm. Now moving towards Proteus simulation. Introducing the components, we have an optocoupler, weight sensor, the main microcontroller Arduino Mega, current sensor, SD card, voltage sensor. So let's start from the beginning. Here we have a relay attached here. What is basically a relay? A relay is just like a switch, but it is magnetically controlled. Why it is attached here? It is attached here to control the voltage. If an excess of current passes through the motor will start malfunctioning. To avoid this, we have added a relay. If the current exceeds its limit, the relay will be turned off. Currently, the relay is turned off, but as soon as we start the simulation, the relay will be turned on if the current is in the limit. Here we have a potentiometer. For example, the relay is off due to exceeding current. So here we can adjust the current and turn back our motor on. Moving towards our first sensor, that is the voltage sensor. Here we have a voltmeter attached. Actually, voltmeter is also a voltage sensor. We have attached it for calibration. If the values of both the sensors are approximately same, then we can say that our voltage sensor is accurate or working fine. The voltage sensor output is going to analog pin 0 of Arduino, and here the voltmeter is attached for the protection of Arduino board, because if a voltage above 5 volts passes through Arduino, our Arduino will get damaged. To avoid this, here we have a diode attached. If the voltage exceeds 5 volts, this diode will cut it off, and here we can get the live display of our voltage. Next up attached to the motor is current sensor. The current sensor, in the same way, here we have an ammeter for calibration purposes, and if the values are same or approximately same, we can say that our current sensor is okay. The pin configuration of current sensor are VCC, Vout. From here the output is going to the Arduino where it detects the current. Here we have a filter, the capacitor to filter out unnecessary signal, and a ground. Voltmeter is attached here for the same purpose, for monitoring the voltage going to the Arduino. Here we have an SD card attached. SD card is a data logging technique, and it is using the real-time track or record from the device. For example, the value at a specific time according to the device at specific hour, minute and second is recorded and kept in this SD card. Here we have a CS pinout, that is chip select. This shows that whether our SD card is inserted in or not. If the SD card is not inserted in, the chip select will give a signal that no SD card is inserted. So we have a real-time clock. It takes data from the sensors and displays it. Then we have an SD card from storing it, and virtual terminal that is connected to the real-time clock. The next up we have an optocoupler. Here we have a switch that is controlling all the circuit. If the switch is turned off, then the whole circuit will be shut down. PC817 is the optocoupler we are using. Here we have an infrared emitting diode, the anode and cathode of the diodes, and collector and emitter of phototransistor. So what actually is happening here? The optocoupler keeps the circuit optically connected but electrically insulated. So it is actually limiting the voltage. Here we have an oscilloscope to display the waveforms when we run the simulation. Actually, let's run the simulation. So this is the virtual terminal. First of all, it will display all the values that are stored in our SD card. The values being displayed are voltage, current at a specific time, RTC, the time that is matching this device. These values are running very fast and we can't actually see the values for a specific time. For that purpose, sdcard.mmc file is placed in these Proteus simulation files. So we can use an app such as Notepad++ for viewing the current and voltage values at a specific time. After it completes showing all the values that are previously stored, then we can view new values. Let's wait for that. Okay, it has started showing the values, so let's check. This is the oscilloscope and waves are being shown here, so let's keep it aside, we don't need it right now. The battery voltage of motor is 10.30, that is from our voltage sensor, and voltmeter shows 10.3. It means that it is accurate. And let's check values for current sensor. It shows 4.49 amperes and our current sensor also shows 4.49 amperes. It means that both sensors are accurate. Now let's check whether the relay works fine or not, because it is the main thing. If the relay is not working fine and current goes up above 5 volts, so it can damage the motor. So let's increase the current and check whether the relay turns off or not. Okay, so now I have increased the current. Let's check whether the relay turns off or not. Okay, so the relay has turned off. It means that relay is working fine. It will turn back on, check whether the current is 5 volts or not, and then go back if it is not. So let's move it to the previous value. Okay, so this thing over here is the counter timer. It shows the number of counts. It is displaying 6, and here is the counter timer is also showing 6.47, approximately 6. It means that both of these are approximately right. Okay, so this was our simulation for motor and its sensors. Let's stop the simulation. Now it's time to see the source code behind all this setup. Okay, so first of all, these are all the libraries that are included in this program. For example, the first one is bio.h. It is for TWI or 12C devices, then RTC library, and then SPI.h, meaning header for serial peripheral interface, and then SD.h for SD card. My file is the file we have created for SD card. Okay, and here we have declared all the pins. I'm assuming that at least you have a basic knowledge of declaring the pins and printing things and all that, at least the basic knowledge of Arduino programming. So here we have declared the digital pins 10 to 13, and here we have declared the analog pins. Here all the variables are declared to get instantaneous value of analog signals that will be used later in the program. Okay, so the first main function in Arduino programming is setup function. Here we will set up the things, for example, the bandwidth of serial monitor. This is serial monitor. The bandwidth of serial monitor is set up at 9600, and then this is the command for printing, print, and then ln means new line. Okay, these are the function definitions. These functions will be used in the program. Here we have declared the input and output pins. For example, these 2 pins are for output and these 3 are for input. Then the second main function of Arduino programming is loop function, that is repeated again and again. Here, first of all, we will check the state of the button, whether the button is on or off. If the button is on and the measure is less than 5 measure, so the measure current is less than 5 and current state is high, so LED will be turned on and it will display motor current overload value. If not, then LED will be off. Then this function is for getting the voltage. Rho is equal to allocate. Rho is the variable that we have declared for getting the instantaneous value. Okay, so this is the map function. What actually a map function is? It's a very good function that is used, for example, the values from range 0 to 1023 will be shown as values from 0 to 20. So map function adjusts these values in between this range. This is the main function. Okay, now the battery voltage of motor is being shown and then DC current is being shown. Then all the things are being stored in the SD card. The file of SD card is named as my file. Okay, all the things are being stored. If the file didn't open, then show that error opening DAQ text. DAQ means data acquisition.txt. Okay, so this whole is commented out because it is for weight sensor and we'll be discussing it with the weight sensor. Next up we have float get DC current. Here in the same way we are getting the DC current, and then here we will function STInt for like whatever we discussed there, that if chip select is not the card is not inserted, then it will be displaying initialization failed, otherwise everything will be going fine, like writing to DAQ text. If the card is inserted, then we'll be writing the things. Okay, next we have is checking that whether RTC is running or not. If RTC is not running, that will be printing RTC is not running, otherwise it's okay. Okay, this is for RTC, for displaying the things. How RTC gets the thing, it gets it from the device, second, minute, hour, day, month and year, and it gives voltage and current values from sensor at this time. Okay, this was our source code behind the program. Now we are left with weight sensor. First of all, let's have a look at how weight sensor actually works. Load cells are attached at the weight sensor. What load cells are? Load cells are strain gauges. When a load is applied on the strain gauges, they either are compressed or tensed. Due to this tension or compression, there is a change in resistance. That change in resistance is recorded and the weight is known to us. The type of circuit used is Wheatstone bridge. Here we have used a Wheatstone bridge. The reason of using Wheatstone bridge is because it can detect very small changes. Here we have used a potentiometer instead of strain gauge because we cannot animate a load and weight on Proteus. That's why we have assumed that the output of strain gauge is the resistance change, and we will change it manually here. Okay. So here it's a load cell in Wheatstone configuration, and here this is INA122 sensor. Let's have a look at what INA122 sensor is. So INA122 sensor is actually an amplifier. The description is written here. The INA122 is a precision instrument amplifier for accurate low noise differential signal acquisition. Its features are it works in 60 microamperes wide power supply range and 8-pin configuration. So let's discuss its basic features. These are the specifications, we will be discussing them, the important one of them. Okay, absolute maximum ratings. Supply voltage needed is 36 volts. The V neg and V positive terminals are 0.3 volts each, negative and positive. Current required is 5 milliamperes. Operating temperature is quite adequate, minus 40 degrees to 125 degrees centigrade. We usually work on room temperatures, and this temperature range is wide enough. What else we have in this data sheet is pin configuration for the sensor. So the pin configuration is that the upper one is V in and the lower one is V in negative. Here we have a gain resistance and here a reference ground, and this V0 is for analog output, which is going to the Arduino circuit at pin 5. So first of all, let's check how the sensor is working or not. Okay, so the weight is 61 and it is showing that item is stolen. So let's move the weight downwards to check what happens. We're changing the resistance, assuming that the strain gauges are changing it. So now the weight is 189 and it is showing that it is safe. So what actually is happening here? The weight sensor design in our case is for anti-theft. So for example, the weight of the object placed is above 180. So I have added a condition that if the weight decreases from 180, then it will be displaying that item is stolen, otherwise everything is safe. So this was the thing that was happening in the background. By changing the resistance, we successfully got the change in our weight, and our weight sensor is working fine.